Welcome to the Problems Channel Season 3, Episode 10, the episode which I titled Infinity in Physics, because in this episode we'll solve a very straightforward middle school physics problem that already requires the introduction of the notion of infinity into physics. But before we deep dive into the underlying physics and mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section under that episode, and I will do my best to find the time to answer all your questions. In this second physics problem of season 3, we're told that a material point, or slightly more practically, a very small ball, or in order to keep the moonlight, a very small spherical chicken of uniform density, is launched from the initial point HO, that is HO units away above the solid and hard or rigid strictly horizontal surface below. The number H0 is known and given. That chicken is launched strictly horizontally with the initial velocity v0, which is known and given, and which also means that the vector v0 is strictly parallel to the hard surface below. Once the chicken is launched in that fashion, it begins its so-called free flight, and at some point it begins bouncing on the hard surface below. The surface is strictly horizontal, it's hard, and we're also told that with every bounce, the vertical component of the chicken's velocity diminishes at a constant known and given rate r, where r is a real, strictly positive number that is also strictly less than 1. And that means that the ratio of the vertical component of the chicken's velocity v after the bounce to the vertical component of the chicken's velocity v before the bounce is precisely r, where r is strictly less than 1 and greater than 0. And that exactly means that with every bounce, the corresponding component of the chicken's velocity diminishes at a constant rate. With every bounce, or during every bounce, there is no friction. And that means that the vertical component diminishes, but the horizontal component, v0, remains 1 and the same and does not change by magnitude. The challenge in this problem is the following. We're asked to find the horizontal displacement of the spherical chicken from the vertical projection of the launch point H0 onto the hard surface below the point O when the chicken stops bouncing. In other words, we have to determine how far horizontally from the vertical projection of the launch point H0 onto the hard surface below will chicken travel before it stops bouncing. And in season 1, episode 2, we explain how to practice mathematics correctly, but the deal with physics is precisely the same. That is, we recommend that just about now. Once you comprehend the problem statement, you put this video on pause, walk away, and try to solve this problem completely on your own and hopefully correctly. As usual, in physics, just like in mathematics, when we want to explain a particular concept, we use the underlying material that is as simple as possible, but not simpler. As such, we take it that in this problem, we ignore the air drag and air resistance, we ignore the potential wind, we ignore the curvature of the Earth, we ignore the fact that Earth rotates around its axis of rotation that is accidentally tilted to its planar orbital plane under the 23.5 degrees. We ignore the fact that the gravitational field of Earth technically changes pretty much at all times, but in our case, we will take it that the height of the launching point of our spherical chicken of uniform density from the Earth level, if you will, is so small that we take the gravitational field generated by Earth to be uniform and constant. And we also ignore the fact that there is technically some friction usually in the real world scenario, but we in this problem ignore friction, and that is why the horizontal component of the chicken's velocity remains one and the same. And under all the possible favorable middle school or high school conditions, when we reduce this problem to the simplest possible scenario, we take it that the mathematical model, remember that in physics we model reality with a particular mathematical apparatus. So under these scenarios, under all the favorable conditions, we ignore many things that I just enumerated. We take it that the motion of our spherical chicken of uniform density is the so-called planar uniformly accelerated motion, and a lot of times I will present a it so happens that in order to solve all sorts of problems where a material point is launched near Earth surface under the ideal middle school or high school conditions, it is actually enough to remember just this one equation shown over here, and pretty much all the material, all different scenarios can be covered just from one this equation. And even though sometimes problems in physics can be solved in a number of different ways, I will stick with this way in this episode precisely in order to imprint on the minds of potential middle and high school students who watch this video that remembering just this one formula is enough. And if you're not familiar with the differential calculus, then that is fine. Take the second equation at its face value just because we said so. But if you are familiar with the differential calculus, then you will see that the equation that expresses the function of velocity of the material point that participates in the planar uniformly accelerated motion as the function of time is shown over here. And where does this formula come from? Well, it comes from this formula that describes how the radius vector of the material point that participates in the planar uniformly accelerated motion behaves itself as a function of time, which here we show the arbitrarily chosen initial vector from certain reference point, then the product of the initial velocity and time, and the constant acceleration times time squared divided by 2. If this function is differentiated with respect to the time t once, then precisely this equation is obtained, because the first derivative of the radius vector over time is the velocity vector as a function of time. The first derivative of a constant vector quantity is 0. The first derivative of this expression is v0. This is what you see over here. And the first derivative of this summand with respect to time is 2 times t over 2. 2 in the numerator and 2 in the denominator cancel each other out, and we have this precise equation. And in our case, the uniform or the same constant acceleration a is numerically equal to the so-called g, or acceleration due to gravity. In physics, a frame of reference or a reference frame is a combination of two things: a coordinate system and a clock. In general, the type of a coordinate system, which could be an orthogonal coordinate system, a spherical coordinate system, a cylindrical coordinate system, or a parabolic coordinate system, or whatever the case may be, depends on the specific nature of the problem, and we usually choose the most convenient one. Moreover, the directions in which the axes of the chosen coordinate system are directed or constructed also depends on the specific scenario. As such, in this problem, we can construct one coordinate system which will be a part of the corresponding reference frame as follows. The initial launch point h0 is projected orthogonally onto the hard surface below, which is a plane that sits at the earth level or sea level or ground level, whatever you want to call it. And this point O becomes the origin of our coordinate system, in which the vertical or the y-axis runs precisely through the points h0 and O thus constructed. And in other words, the angle between the vertical or y-axis, whose direction we take to be this one right here, showing pointing upwards this way, this will be the y-axis, is precisely 90 degrees or pi over 2 radians with respect to the underlying hard surface, which again is a plane that is at sea level, let's say. And in that plane, we will choose in some direction the axis which will play the role of the horizontal or the x-axis. And this axis will be pointing this way. This will be x. And again, in theory, to be good mathematical citizens, we also need a unit of distance on the x-axis and the unit of distance on the y-axis. Let's pretend that this unit is given, and in this unit we measure the initial height h0, and in the same units we will measure the horizontal displacement that is sought after in this problem. Now that the coordinate system, or altogether a reference frame, is chosen and constructed, what we do is we take our main equation of motion. At this case, at this level, we'll call this the equation of motion at the, let's say, middle school and high school level. And what we do is we project this equation onto both axes. In general, you would want to project your equation onto as many axes as you have in your specific problem. In the one space problem, there will be one axis. In the two space problem, as we have here, there will be two axes. In the three space problem, there will be three projections, and so on. So if we project our equation of motion shown over here for the radius vector onto the y-axis, what will we have? We will have the following expression. The coordinate, the vertical coordinate y will be a function of t, which is what? The initial displacement of our launch point along the vertical y-axis is h0. The vertical component of the initial velocity is what? is 0, so we do not write anything, and we take it that our uniform or constant acceleration in this case is due to the Earth's gravity. It will point this way. This acceleration is usually denoted with g, and since technically the projection of this vector onto our vertical axis will be what? The magnitude of the acceleration due to gravity times the cosine of the angle that this actor forms with the corresponding axis. The angle in this case is pi. The cosine of pi is -1. So this is what we write: minus gt squared over 2. Wonderful. What is the corresponding projection of our equation of motion for the radius vector on the x-axis? Well, the horizontal coordinate changes with time. Which way? Well, we're told that the motion along the x-axis is only due to this initial velocity. So this will be v0. Remember that again, the cosine of the angle that this vector makes with the axis onto which we project our vector v0 is what? 0. Cosine of 0 is 1. Consequently, we'll have v0 times t. Wonderful. This takes care of the radius vector. Now let us project the velocity vector onto the corresponding axis. What will we have? We will have for the vertical projection, Vy of t will be what? The initial velocity here, v0, on the y-axis is 0. The projection of our constant acceleration, as we explained, will be negative gt. And for the horizontal component of the velocity of the chicken, we get what? Precisely, we get one and the same number, v0. And from this material, it's already enough to study what will happen to our chicken prior to the first bounce. In other words, the initial bounce will take place at the distance, let's say we'll call it x0. And how do we recover the magnitudes of interest in this case? Well, let us do the following. From this equation, it follows that for the time expressed in terms of the locally available material, we have x divided by v0. That much is understood. Wonderful. Now we take this result and we put it into the equation for y. Why is that? Well, we want to find the shape of the function y of x. And under that maneuver, what will we have? We will have that y, this time of x, will be h0 minus g over 2 v0 squared times x squared. And what is this equation over here? Well, evidently, this is the equation of a horns down parabola, and in this case it will be the right arc, the right parabolic arc, that explains this behavior of our chicken this way, because x varies strictly from which way? X will be greater than or equal to 0. So the minus sign over here precisely in front of the x squared is precisely what explains the fact that this a horns down parabola, or the parabola whose horns point this way. And again, here between this fully symmetrical parabola, we only choose the right parabolic arc precisely because x varies from 0 and onward. Wonderful. Now that we have this equation over here, let's underscore it this way. How can we tactically spin it to our advantage? Well, let's think about it. What will happen at the first touchdown when the chicken touches down the hard surface below for the first time? Well, look at this. The vertical coordinate of the chicken will be what? 0. Consequently, if we put here for y of x, we put 0, we go this way, we put 0, then we will have h0 minus g over 2v0 squared times x0 squared. You see the x0 squared is this magnitude shown right here. In other words, x0 represents the horizontal displacement of our brave chicken from the origin of our coordinate system, which is what? Which is an orthogonal projection of the launch point onto the surface below. This distance right here, x0, and we can already solve this equation over here. Technically, it's a quadratic equation, but in this case, what do we have? We have x squared 0 times g over 2v0 squared is equal to h0. Would you agree? From here, x squared 0 is equal to 2h0 over g over g times v0 squared. That much is understood. G went into the denominator. 2v0 squared went into the denominator, 2v0. Now we take the square root of both sides. We have plus minus v0 square root of 2h0 divided by g. And between two signs that we obtained, which one do we pick? Precisely in our coordinate system, this direction is positive. So this number right here, x0, corresponds to the positive selection. And this is our first result. You can write it down. We will use it in a few minutes. And how do we spin the situation further? In some sense, technically, we can move on already because we have what we need, but this is another pedagogical advice for our viewers: is every time you take on a problem in mathematics, physics, or computer science, it doesn't really matter. Yes, definitely you want to answer the question posed in the problem, but as my personal suggestion, and that is what I used to do and still do to this day, I always try to expand the radius of coverage of the material that I can excavate or answer. In other words, whenever you take on a problem in mathematics, physics, or computer science, try to answer more questions that are posed in the problem officially. Sometimes you will not be able to do it, sometimes you will, but the effort, the impetus to do that will benefit you academically greater down the road. As such, in addition to the horizontal displacement of our brave chicken from the origin, what we can now also deduce. Once we have that, we put this number into this formula over here, and what do we have in this case? Known quantity, unknown quantity. So here we take this result and we put it over here, and then what do we deduce right away? Let's write it down over here. The t0, or the time that our chicken was airborne as it was traversing the first parabolic arc towards the touchdown, towards the eagle has landed, will be given by what? Will be given by the ratio of the x0. Let's write it down. It will be x0 divided by v0. And in this case, it means what? t0 is equal to, we divide this result by v0, and look at this. As if by magic, almost automatically, we obtain our result. 2h0 divided by g. Write down this result. We will need it sometime later. And the last thing before we move on to the next segment and study what happens after the first bound, after the second bounce, and so on, what else can we do? Well, let us carefully look at our equation shown over here. If we know the time of flight, t0, then if we put this time t0 into this formula, what will we have? precisely, we will know the magnitude and the direction of the vertical component of the chicken's velocity immediately before it touches the ground, if you will, immediately before the first touchdown. So now let us, if you guys understand the deductions, it looks like I don't have any more room on the board. I will erase some material over here. I'll give you the time to put this video on pause, keep your records straight, but the idea is very straightforward. We take this number t0, we take the right hand side of this expression and we put this result into here. You see this result into here. And when we do that, what will we recover? We will recover the magnitude and we will know the direction, of course, of the vertical component of the chicken's velocity immediately before the first touchdown. So let us do just that. I will erase, let's say, this part over here. You guys should be able to reproduce it on your own or rewind this video. But now let us execute this maneuver. Look at this. This goes into here, and then what will happen then? It will be minus g times square root of 2h0 over g. And that means what? If we move one copy of g under the square root, what will happen? G will turn into g squared, and g squared in the numerator will cancel out. Let's do it this way together. Minus square root g squared times 2h0 over g. You see the maneuver g crawls under the square root, gains one extra power, g squared, and now second power, and this cancel out. And what do we have? Let's write down this way. Vy1, let us agree that with Vy1, we will designate precisely the vertical component of the chicken's velocity immediately before it executes its first touchdown. This will be V10, this guy. So what is this? It's minus square root of 2gh0. Remember this result as well. You see, this segment is very rich with technical material. We excavated quite a bit of useful information. We know the horizontal displacement of our chicken with respect to the origin at the first touchdown. We know how much time the chicken was airborne prior to the first touchdown, and when the chicken touches the ground for the first time, we know exactly its velocity right here. This is the expression for the velocity. And now that we understand what transpired prior to the first touchdown, we can analyze the interesting things that happen immediately before, during, and after the first touchdown. Wonderful. Now that we understood how did the chicken get to its first touchdown, let us study what will happen after the chicken takes off the ground for the first time. That is, at the point where, let us study it more carefully right here, for example. At the point, let's pretend that we move this point over here, just for the demonstration purposes. What do we have over here? Well, our initial horizontal velocity of the chicken remains the same. Why is that? Well, we're told so because there is no friction. There is no friction during the collisions between the chicken and the hard surface. So the green horizontal velocity vector v0 remains one and the same. It does not change. The magnitude of the vertical component of the chicken's velocity when it hit the ground, we already just computed, and we refer to it as Vy1. We said that it is minus or negative square root of 2gho. Why is that? Well, in our case, the vertical axis points this way. The vector of the vertical component of the chicken's velocity points in the opposite direction. Cosine of pi is -1. Boom, there we go. This is the minus. What is the total velocity of the chicken when it hits the ground as it hits the ground for the first time? Well, it is a vector sum. So technically what we do is we use any one of your favorite rules of adding vectors, but this is the vector of the total velocity of the chicken as it hits the ground. And let's say this angle right here, let's say angle theta 0. What can you say about this angle? Can we compute this angle? Of course we can. Let us carefully sneak it in right here. The tangent of the angle theta 0 will be what? It is the magnitude of the opposite side, which by absolute value, let's say, so we don't have to deal with the negative signs, will be square root of 2gh0 divided by the length of the adjacent side, v0. So we know quite a bit at this point. However, what are we told about the collisions of the chicken with the hard surface? We're told that because there is no friction, the horizontal component of the chicken's velocity does not change at all. It remains v0. But we're told that the vertical component after the bounce diminishes by the same rate with respect to the vertical component before the bounce. That means that, let us carefully note this, and of course I will exaggerate it to a great detail just to imprint it onto the minds of our viewers that that is the case. Look at this. This is with Vy1, we will designate the velocity of the chicken as it immediately before and let's say during the first touchdown, and we computed the velocity minus this square root right here. But at the moment of the collision, the velocity vector that keeps track of the vertical component of the velocity flips to its opposite, but while this direction changes, when the collision is absolutely rigid, the velocity flips to the opposite direction and keeps the magnitude, but here the magnitude does not stay the same, so the collision is not entirely rigid. There is a loss of velocity, and we know, see exactly what's going on here. We are told how that change unfolds. We're told that in this case, at this point, the vector that I show with the red color is what? Is the initial vertical velocity of the chicken as it takes off right here, as it takes off for the first time and enters the next leg of its journey. And what is that velocity? Well, we will refer to this velocity as Vy1 after the first bounce, comma 0. I know it's a little messy, but I think that's the smallest compact way to do things. And then what happens? Well, if we add these two vectors together, remember that the horizontal velocity v0 remains the same. Now the angle under which our chicken will take off, it will be theta 1. What can we say about the magnitude of this angle? Can we compute it? Yes, we definitely can compute it, and that angle, at the expense, at the risk of overloading this discussion with too much information, let's say, but just because we can, let's do that. What will be the velocity of the velocity, the vertical component of the velocity after the first bounce as the chicken takes off. Well, we're told that it's r times the velocity, the vertical velocity immediately prior to the first touchdown. We know that. So by magnitude, this will be what? This will be r times square root of 2g h0. Game over. We know what it is. So the value of the trigonometric function of tangent for that angle is already known to us. It's this guy times this guy. So it is basically r times the tangent of this guy. Let's write it down. It will be r times square root of 2g h0 over v0. So now you guys understand what is going on. This is the semicolon over here. So now that we understand what is going on, and some of our viewers probably already see what's going on. After the second such bounce over here, what will be the value of the Vy20? Well, it will be r times this guy, but this guy is r times the velocity prior to the first bounce. So here will be r squared for the third bounce, r to the third for the fourth bounce, r to the fourth, and so on for the kth bounce. It will be r to the kth, but let us not get ahead ourselves, but let's deduce all this information officially. Again, in this case, we take one and the same trusty law of motion, let's say middle school or high school law of motion, and we project it onto the axis of the constructed reference frame. So what will happen in this case? Well, let's carefully write it down. For the y component that changes over time, what will happen? The initial displacement vertically is what in this case after the first touchdown is 0. Exactly. So what is the initial velocity? Well, we already know what it is. It will be Vy10 times t, and the projection of the uniform acceleration, again, cosine of pi is -1, so it will be still again minus gt squared over 2. What will we have for the horizontal displacement? Again, let's temporarily ignore the fact that our frame is over here. We will get back down in meaninglessly boring and convoluted arithmetic. Let's shift everything over and pretend for now that this is our initial takeoff as it normally would, as if a material point is lodged under an angle, which we already know, to the horizon over here, just because we want to get the basic idea of the trajectory, of the shape of the trajectory. Remember, the shape of the trajectory prior to the first touchdown, we already know it's an arc of a horns down parabola. We proved that. Now what will happen? Well, let's do this. The initial velocity horizontally will technically be what? Vx1, 0, the initial, but we already know that from the problem statement it follows it will be that velocity will be one and the same. It will be v0 times t still. And what will we have for the velocities? Well, vy of t will be what? It will be our velocity vy10 minus gt. That much we understand, because again, the vector of the acceleration due to gravity g forms the angle of, let's say, pi, the smallest angle pi, with the vertical axis that points technically upwards, and the vector for the acceleration due to gravity points downward. That is why minus. And what do we have for the x, for the horizontal component of the chicken's velocity? Well, technically it's the same horizontal velocity v0 plus a times t. I did not mention it in the previous segment, but we all should understand that when we project the vector of the acceleration due to gravity onto the x-axis, how do we do it? Well, we have to multiply the magnitude of that vector by the angle which this angle forms with the axis onto which we project that vector. And what is that angle? Well, that angle is, again, pi over 2 radians. The value of the trigonometric function of cosine evaluated at pi over 2 radians is what? 0. So here we have technically plus 0 times t, and that is 0. Wonderful. Now we have all this material. What do we need? Our goal is to compute this distance right here. This distance, let's call it x1, or the distance that our chicken will travel. The distance that our chicken will travel after the first bounce, as it approaches the second bounce right here. How do we do it? Well, first of all, if we, from this expression, again, remember, if we say that t is equal to x over v0, we put it, the result of t, we put it from here into here, then what will we have? Let's write it down. Over here, we will have y of x is equal to v y1 0 times, instead of t we put x over v0 minus g over 2 v0 squared times x squared. Again, the magnitude of y1 0, that is this red vector right here, what the magnitude of the vector, we know that's what it is. It's r times the magnitude of the velocity before the touchdown, and we know what it is here. So in terms of the given material, this question is completely answered. So here again we see that the shape of the trajectory that our fearless chicken will traverse after the first bounce will still be what? A parabola which has what? Horns down. The minus in front of x2 shows the horns down parabola. We'll show it this way. And now that we understand the shape of the trajectory of our chicken after the first bounce, which is a horns down parabola, we want to compute basically this span that parabola makes with the x-axis, or the distance x1. How can we do that? Again, that is quite straightforward. When the chicken reaches, let's take this one. Let's agree that this will be the highest point right here. We will name that point, let's say h1, the highest point to which the chicken will climb after the first bounce, h1 over here. How can we compute that distance and the time, and consequently the horizontal distance that it will travel? Well, at that point, at this point right here, look at this, the vertical component of the velocity will vanish, because again at this point the velocity will point precisely this way. Our velocity v0 will point this way, so the horizontal component at this time vanishes. So if 0, let's say we'll grab this equation, 0 is equal to vy1 0 minus gt1, and with t1 we will designate what? With t1 we will designate the time that it takes our chicken to climb to the pinnacle of its career over that parabolic over the second span that it will cover over here. The first span, and this will be the second one. So from here, once we solve this equation from here, it follows what? That GT1 is equal to VY10. VY10 is known by magnitude over here. So let's write down, so from here it follows that the climbing time T1 that the chicken will take in order to get to the point H1 will be what? It will be VY10, so this guy R square root of 2GH0 divided by G. Remember, see, from this one, T1 is equal to VY10, which is known, divided by G. Now, if we bring G under here, see, like this, what will happen? Again, this G would want to sneak under the square root. And as it does so, it will gain one extra power. And the G squared, let's write it down here, it will be R times square root 2GH0 over G squared. I apologize for the mess. In a few seconds, I'll take a short break, guys, and I will erase this material and make things to make room for the deductions that we will do. So here, one copy of G in the numerator and one copy of G in the denominator will cancel each other out. And what does it mean? Let's jump over here, guys, and write down this result over here. T1, this is the time. This is the time for T1. I'll write it down right here. T1. Let's agree for the designation. The time T1, lowercase t1, will be the time that it takes the chicken to climb to the highest point of the parabolic trajectory after the first bounce right here. So this is the time T1 will be R times the square root of what? 2H0 over G. This is the result that we now obtained, and now the rest of the manipulations that we'll carry out in a few seconds should be transparent. If we know the time T1, then we know the time that the chickens spent airborne during this arc of its journey. It will be simply twice. 2 times lowercase t1 will be, let's say, uppercase t1, the time that the chicken took to fly towards the second bounce. And once we know that time, we know the velocity, boom, we know the horizontal displacement. So for now, let me take a short break, erase the material over here. This material should be straightforward for you. If you have any questions, do ask. But the idea is, again, observation. The key observation here is this: from this equation, we see that at the highest point of the chicken's trajectory here on its second leg, it will be 0. Momentarily, this component will vanish. So from 0 equal to Vy10 minus GT1, we find this time T1. And this string of manipulations should also be straightforward. This is directly from the problem statement. This is how we take the problem statement. The vertical component of chicken's velocity diminishes at uniform rate. What does it mean in symbols? Well, this is what it means in symbols. And then boom, we derive our result for the time t, lowercase t1, that it takes the chicken to climb from the ground level up to the highest point h1 of its first complete, so to speak, bounce, or one complete parabolic trajectory. Now that I erased some material on the bottom right-hand side of the board for our final journey through this segment, I kept our projections not erased so you can see it. And here again, let us agree that with the uppercase T1, we will designate the entire time that the chicken spent airborne as it was completing the second leg of its journey, from the moment it took off from the hard surface after the touchdown number 1 until it fearlessly soared through the sky up into the point H1, came down into the point of the second touchdown. So T1 is the entire flight time between the first touchdown and the second touchdown. What is this time? It is twice the time that it took the chicken to climb to the highest point, to the pinnacle of its flying career over this leg of its journey. That is it. That motion is because the trajectory is symmetrical with respect to its axis of symmetry. So are the times. The physics of this motion works out that way, and we can write down the result for T1 right away. It is simply 2 times r times square root of 2h0 over g. That much should be clear. If you have any questions, the comment section is open. Be my guest. Now we instantly recover what? From this equation into this equation, we put this result because the velocity that in some sense controls the motion along the horizontal axis is known. And by the way, the planar motion over here that our chicken exercises, again, depending on what comes first, again, the chicken or the egg. If we have the axis first, then we'll launch the chicken along that axis. If we are not given the axis and we want to construct it, look, we have 3 distinct points: h0, the point where the vector v0 ends, and our point O. 3 distinct points define a unique plane. Boom, this is the plane. This is where the chicken goes through its bounces. Wonderful. So here, from this equation, let me carefully, well, let's do it this way. You guys can see it from here. We do this, we merge this result and this result. So x1 is equal to v0 times t1. That much should be understood. This is the straightforward arithmetic of that motion. From the projection of our radius vector onto the x-axis of our reference frame, it follows that at the time t1 that the chicken spent in the air between the first touchdown and the second, it will cover this distance, and voila, we write down the result. It's not complicated. Let's do that. It will be v0 times this number, so 2v0r, and what is the square root? 2h0 over g. Game over. And the last question again, because remember, we want to do with every problem in mathematics, physics, computer science, whatever we deal with, we want to try to do more than we are asked to do. That is my fancy interpretation of increase the radius of the material that you cover with your answer. Excavate and try to dig more. Sometimes you will succeed, sometimes you will fail, but this effort, this impetus will benefit you academically down the road. Now, the last question is, what is the magnitude of h1? Here, the magnitude of h0 is given. What is it here? Again, just to come through on my promise that I made earlier at the beginning of this episode, this is the one equation that you need. I will show you how you can derive this, the answer to this question, what is h1, using nothing but this, or actually this, but this is not how I would personally do it. Again, this channel is not about me. It has nothing to do with me. This channel is about studying academics for the sake of studying academics. And again, academically, the viewers in our audience who pay attention will say, Roman, why do you go through this error-prone and boring computations when you can cut to the chase with, drum roll, the law of conservation of mechanical energy? Exactly. We can compute h1 almost instantly from the law of conservation of mechanical energy. mv squared over 2 is equal to mgh. Game over. Yes, correct. That's how you should do it. But also, you should try to carry out this computation also with me to see how two different lines of reasoning in physics converge into one correct answer. As such, let's hijack in a good way this thing right here. What will happen? H1 will be equal to Vy10 times T1 minus GT square 1 over 2. That much you should be able to understand on your own, and that is exactly why I said this is all you need for the bulk of the problems where something is launched under an angle to a horizon somehow. Near Earth gravity, absence of wind, absence of drag, air resistance, no curvature of Earth, no Earth spinning. Velocity v0 is way less than the velocity of light. No relativistic physics. Toy middle school conditions. Bam, bam, bam. We know the answer. So here, let's carry out this mundane computation together. Let's do it this way. So we know the value of Vy10. What is it? It is r square root of 2g h0. What is T1? T1 is r, so square pops up. Now times square root of 2h0 over g minus g over 2, g over 2, g over 2, and this bad puppy squared. R squared times 2h0 over g. You see, this is middle school arithmetic. The g in the numerator and g in the denominator, both square roots, cancel each other out. Cancel. Square root of 2ho times square root 2ho is 2ho. So what do we have? We have r squared times 2ho minus what? 2 and 2 cancel out. R squared ho, and in the end we have r squared ho. You see? This is it. Again, we could have obtained that result, like I said, from the law of conservation of mechanical energy right away, but let us write down this important result. H1 is equal to r squared ho. We need this, we need this, we need this, and where is this guy? We need this. Once you understand where did these results come from, you practically solve the problem, because now, as more and more bounces unfold, as our chicken fearlessly soars through the skies and bounces around the hard surface, it's basically rinse, floss, rinse, repeat. It's the same thing. What will change? The only thing that will change in all the computations that we will be carrying out is what? Correctly, the only thing that will change in all the computations that we carry out is the power of the real number r. Power of the real number r. For x1, it's r to the first power. For t1, it's r to the first power. But remember, this is the key relation over here, because as we tack on more and more bounces, what will we have? Well, let me take a short break over here. I will erase this material and prepare it for the study or the analysis of the case when our chicken executes our second complete bounce. As I said a few seconds ago, the behavior of our heroic chicken during the second complete bounce between the touchdown number 2 and the touchdown number 3, this parabolic arc will be essentially or fundamentally the same as the behavior of the chicken during the first complete parabolic bounce. And that is why if we understand the behavior of the chicken between the touchdown number 1 and the touchdown number 2, and I hope we all do, we spend the entire previous segment developing that understanding, we can simply mechanically carry out the computations for the second bounce. And just about the only thing that we need to be careful about over here, let me erase this a little bit, is the following. The initial vertical velocity with which our chicken will take off over here will be Vy20. So Vy20 will be R times Vy10, which itself was what? R times Vy1. Remember that? That is how, this is the little factory that produces the elements of the so-called geometric progression. We understand that this will be R squared. So for the second takeoff, the vertical component of the chicken's velocity for the second takeoff will be 2. This will be square over here. Why this is important? Well, this velocity, remember, goes over here because now when we project all our equations, we simply mechanically replace 1 with 2, 0, what else is 1? Here, instead of 1, it will be 2, 0, you see? This is how, from this equation, remember, we recovered the climbing time. And what is the climbing time to? Well, that will be the climbing time to here, to this point, h2. This will be a lower point. And this time, this will be t2, the time that the chicken spent climbing up to that point over here. And what will be here? It will be t2, but t2, remember, is expressed via Vy20, which has what? R squared, so square. Consequently, t2, or the time during which the chicken was airborne for the second complete parabolic bounce, will be twice t lowercase 2, and that will be here again. We erase this. This will be t2. This will be square. Consequently, for x1, we will have x2. This will be t2. And what is x2? It's this distance right here, x2. Well, let's be careful, students of physics and mathematics. This is x2 right here, this distance. This distance, this distance, this distance, and this distance. T2, but T2 has the second power, so this will be square. And consequently, for the computations for the highest point, H2, we will have 2, we will have 2, we will have 2 over here, 2. And once you carry out all these computations, this will be actually to the 4th power. This will be R raised to the 4th power, 4th power, 4th power, 4, 4. This will be 4. And then H2 will be R raised to the 4th power time H0. You see, fundamentally, there is we should have no problems deducing all these results. This is all mechanical carryover of the first case into the second case, and so on, into the 3rd bounce, 4th bounce, 5th bounce, and so on. And right now, since you guys understand how we do it, the technology is quite simple. Project, express t for x, put it into the first expression, prove that the trajectory of our heroic chicken will be horns down parabola. This is done. Equate the vertical component of the chicken's velocity Vyt at the highest point of the corresponding complete bounce to 0. Deduce the climb time from here. Once the climb time is known, multiply it by 2. Then take the corresponding horizontal displacement, horizontal span of the parabola, multiplied by v0, obtain the horizontal distance that the chicken traveled, and you can also obtain the vertical, the rise, so to speak, how far up did the chicken climb during the corresponding bounce, and the game is over. Notice that, look at our times. Times go as square of the ratio that we're given. The velocity goes as a square. The distance changes as the square of the ratio, but what about the height? Well, the height apparently diminishes even faster because it's even power, always even power, 2 times something. So let us now, I will take a few seconds to erase this material. You guys should be at home with all this technology that we developed. So now I will just state the results for what happens to the chicken, what is the behavior of chicken during the third complete bounce. One more time, in order to make sure that all the viewers in the audience understand what is the source of this little engine or of this little factory that produces the elements of the geometric progression. Here is the following. The vertical component of the chicken's velocity as it takes off for the third time is r times smaller than the corresponding velocity with which it took off during the second bounce. And again, by the law of conservation of mechanical energy, I erased this vector diagram, but you should be able to reproduce this vector diagram on demand on your own. At the at the point of the second touchdown, the vectors by magnitude will be here immediately. At the touchdown will be the same. This vector at takeoff will be the same as the actual vector at landing. That is why this relation comes into place. But this velocity itself is r times the same velocity on the previous bounce, which is what? Which is r times the velocity, the vertical component of the chicken's velocity immediately before the first touchdown. 3 copies of r. In other words, the vertical component of the chicken's velocity at each interesting touchdown. In this case, at the third touchdown will be r, the one and the same ratio raised to the third power times the magnitude that we already deduced, square root of 2gho. And from that point onwards, all the interesting magnitudes roll down or come out of the horn of plenty, as we explained. At the top point of each parabolic arc, the vertical velocity, the vertical component of the chicken velocity vanishes because it is precisely perpendicular to the y-axis, and the cosine of 90 degrees is what? Is 0. That vertical component, I'm sorry, the magnitude of this component, of the vertical component, vanishes. And then from that point, from that observation, we recover the time to climb to the highest point over here. So the total flight time after the after the third bounce will be twice the climb time to the highest point at the third bounce over here. It will be 2r cubed times the square root of 2h0 over g. The distance, this distance right here, this span that the chicken will cover horizontally, x3 from here to here, is given by v0 times that number. We take it from here and then we introduce v0, but the power is the third. And for the height of the highest point during that bounce, we get the sixth power, which is what? Which is 2 times 3. So in some sense, we can see that as the corresponding velocity, airborne time, and the horizontal distance, these all magnitudes diminish proportional to the third power here. The height actually diminishes way faster at twice that rate. And now that we understand what happens with the bouncing chicken on the third leg, we can generalize this and mechanically again replace 3 with a generic number k that varies between 1 and n. I think that I explained the material of why things happen the way they happen slowly enough and thoroughly enough in the previous segments. But if you have any questions, then do not hesitate. By all means, the comment section is open. Ask away. And at that point, we should all understand that after the kth bounce, or after the bounce number k, the velocity with which our chicken will fearlessly soar through the skies will be given by this expression, r raised to the kth power times the square root of 2 times g, acceleration due to gravity, times h0, the initial height. The time that the chicken will spend airborne during that bounce is given over here. It's twice the time that it takes the chicken to climb to the highest point, half the time, overall time to ascend, half of the overall time to descend. So that will be 2 times r raised to the power of k times square root of 2 times h0 divided by g, acceleration due to gravity. The horizontal span that the chicken will cover during that bounce, xk, will be v0 times tk, this time right here. So this result is mechanical, 2 times v0 times r raised to the power k times square root of 2 times h0 over g. And the height k, the highest point for the during the kth bounce, will be h0 times r raised to the power 2 times k. That's important, 2 times k. So the heights actually diminish faster than these 3 magnitudes over here. And correspondingly also we had an interesting relation for the tangents of the angles that the vectors of velocity make with the horizon. But we now understand that the horizontal displacement sought after as our chicken bounces along the x-axis will be represented as what? The initial horizontal displacement x0 plus the sum of the horizontal displacements xk, these guys right here, where the k runs from 1 to n. And the interesting question is, what is n? What is this number? And it turns out that many students bring this problem to this particular point. They can bring it here, but this is the point where they get stuck. And at this point they say, we do not know what to do, because what is that number? What is that number? Coming up with specific number 3, 17, 21, 5000 doesn't really feel completely correct from the theoretical standpoint. And here, in order to answer that question, I will direct your attention to the physics problem that we solved in previous season at the end of season 2, where we were asked to compare what is more difficult or more easier to tilt or flip over, a cube or a comparably sized right circular cylinder. In that episode, we'll learn that overall the fundamental approach to solving problems in physics was as follows. We take the problem framed in the local tongue, then we translate the local language into the language of physics, then we translate the language of physics into the language of mathematics. We solve the problem in mathematics and we roll backwards. We translate the local mathematics into local physics, and then we translate local physics into the local language and make this complete round trip. So here, when we get stuck, because we think, okay, so far all our reasoning is correct, we never made any mistakes anywhere, but what is n? How far do we take our sum and our bounces? Well, the answer to this question, again, remember, we took the problem framed in the local language. In English, we translated English into physics, physics into mathematics. Here is the mathematics. But how do we how do we determine what is the value of n? And here again, we go back to this advice and we need to translate the words, the soft, the chicken stops bouncing. We need to find a way to translate the soft English or whatever your favorite, whatever your native tongue is, the soft phrase stops bouncing into hard, concrete, and actionable mathematics. Well, here's one way to translate soft stops bouncing into hard, concrete, and actionable mathematics. We know that the maximal height to which our chicken fearlessly soars through the skies against all odds is given by that expression over here, and it can be said that our chicken will stop bouncing when it fails to get airborne, or precisely when the maximal height to which this ascends will be what? Will be zero. In other words, we need to manufacture a situation where there exists, this is a mathematical term, the so-called existential quantifier, but okay, it doesn't matter. There exists a whole positive number n such that the maximal height to which our chicken will ascend on that particular bounce raised to the power 2n will be 0, because then mathematically if the highest point of the chicken's trajectory is 0, then definitely it's not bouncing. Not a little bit, not itsy bitsy, insy wincy, little something, nothing. Out of all the possible points, we find the highest one and we bring it down, we nail it to the floor, and we say, listen, that's it. No more bouncing around. And at that point, it is completely legitimate situation that under which we can say that the chicken stopped bouncing. You see, stops bouncing, the maximal height is 0. But right now, as it stands, this expression over here represents the so-called mathematical heresy, because under no finite scenario this equation can be satisfied, because h0 is a finite positive real number, r is a finite positive real number, so is 2, so is n. This can never happen. But the question, when can it happen? This is where and how infinity enters the world of physics. Here, this is one of the typical early exercises that you will be asked to complete on your own, probably within the first couple weeks of your real analysis course in college, probably first semester, first year real analysis course. You will be asked to show that the limit, now that we introduce the limit when n grows without bound to positive infinity, and that's how infinity enters physics, then this expression over here completely makes sense and is perfectly fine when the absolute value of r is strictly less than 1. This is how mathematics works out. Then, in this case, when r is 0, r is strictly less than 1, then the limit will be 0, and that is how precisely the notion of infinity, in this case positive infinity, enters the world of physics, as the title of this episode claims. So now, once we understand that if this is the case, then under these conditions, that is how the chicken will fail to get airborne at all, the highest point of its trajectory will be 0. And that precisely means that it will stop bouncing. But that exactly, again, what does that mean over here? Well, in theory, yes. In physical, tangible world, nothing is really infinite. It will be some number, but theoretically, remember what we do in physics, we obtain the computational goal of theoretical physics. We studied this earlier too, is what? Is an exact solution of an approximate problem, and an exact solution means precisely the work within the confines of a chosen mathematical model. So what we have is a mathematical model, and this here expression represents precisely that, a mathematical model. So now we have our answer. What we have over here is not a finite geometric series, but an infinite geometric series. And at this point, we develop the answer fairly expediently as we write what? We factor out v0 and the square root. v0 and the square root of 2h0 over g. And what do we have? 1 plus the sum that varies from 1 to positive infinity of r, where k raised to the power, r is raised to the power k, positive infinity. Again, this is how infinity enters the world of physics. As we can see, the material here is thoroughly middle school. This is all thoroughly middle school, maybe upper middle school, lower high school material, nothing fancy, but already this situation forces us or suggests the introduction of the notion of infinity into physics. And that is how one way, using the very straightforward material, and that was the whole idea why I put this episode together, using a very simple language, a very simple vocabulary, physics vocabulary, that does not span beyond, like I said, middle or high school curriculum, will already necessitates the introduction of the notion of infinity, which is a mathematical notion. So now we know how to sum the infinite series. And now we have it, v0 square root 2h0 over g, 1 plus, and what did I forget? I forgot 2 over here, 2 times r over 1 minus r. And what do we have over here? 1 minus r plus 2r over 1 minus r. Would you agree? 1 minus r jumps in the numerator, plus 2r, negative r, and this and 2 copies of r cancel out. And what do we have in the end? In the end, we have v0 square root of 2h0 over g times 1 plus r divided by 1 minus r. This is precisely the horizontal displacement sought after. Precisely at that distance, our heroic chicken, will stop bouncing. And again, this is how theoretical physics works. We have actually two numbers over here. One is a theoretical number, the other one is practical. This is our fearless theoretical prediction. If you give us specific numbers for v0, for g, for h0, for r, and conduct the experiment in such a way that it honors this behavior: no friction near Earth gravity, no wind, no drag, no air resistance, curvature of Earth, chuck it, the rotation of Earth, chuck it, relativistic physics, no good, very slow velocities, uniform gravitational field. In your case, and you put these numbers into our formula, you will come up with a number, some number, something. That is theoretical number. With a experimental number, you will have always what? You will have some number, always plus minus some epsilon, some error. You will also have for v0, you will have plus minus, well, for the horizontal, another error rate for the velocity. You will have some error plus minus for the gravitational constant, the so-called acceleration due to gravity. What else? You will have plus minus 4r. It will be some number that you will establish experimentally, but it will be epsilon for r. You will measure the distance. Somehow you catch the number here. Boom. This is the x number where the ball start bouncing. This will be the number also plus minus some epsilon of that deals with x. When you combine all these results, this number, and this is how physics and hard science works, our fearless prediction is this number will be dearly close to the number that will be produced by our theoretical computations. And now we can bring the problem home and compute what we can compute the total, for example, vertical distance that our chicken traveled before it stopped bouncing and the time that it spent in the air while doing so. That is because our chicken participates in the frequent flyer miles program. It is entitled to a free computation of the total vertical distance that it traveled prior to failing to take off. And we know that the maximal height hk that our brave chicken fearlessly soars through the sky 2 on the kth bounce is given by what? h0 times r raised to the power 2k. We know that the total vertical distance that our chicken will travel will be comprised of what? The initial vertical journey on the downward parabolic arc over here, h0, plus 2 copies of each maximal height hk. Why 2 copies? Because first the chicken will ascend. First time it will cover this vertical span on the ascent to that height, and then the second time it will be covered when the chicken descends again fearlessly towards the next touchdown point. So 2 copies of this height hk. So the horizontal displacement we captured over here. This is for your reference. And now with this sum, we also know how to deal with. We factor out the common term h0 and we get 1 plus 2 times, what is the sum? It will be r raised to the power squared, r squared, minus 1 r squared. And then what does that mean? That means that we will have h0 times, let's do this together, 1 minus r squared jumps into the numerator, plus 2 copies of r squared still in the numerator. In the denominator, 1 minus r squared, negative copy and positive copy cancel like so. And what do we get? 1 plus r squared over 1 minus r squared. In other words, the total horizontal distance, the total vertical distance traversed by our brave chicken is given by this expression over here, h0 times 1 plus r squared divided by 1 minus r squared. This is the total vertical distance that our chicken travels up to the point when it stops bouncing. And next we can do the same to the total amount of time that the chicken was airborne as it executed its bounces. Lastly, because this is part of the package deal, because our fearless chicken participates in the frequent flyer miles program, we compute the total time that was airborne and accrue more savings on the credit card of our clever theoretical physics major chicken, spherical chicken of uniform density. We know the time that our chicken spent descending from the height HO to the first touchdown shown over here. We know all the consequent times of complete bounces that the chicken makes. This is our formula shown over here. And in some sense, we know that 2 over here, the factor of 2 in front of this time, where r is raised to the power of k is explained which way. The time that it takes to climb to the highest point is exactly the same time as it takes to descend from the highest point to the ground level. That's why we have 2. And now we simply evaluate this here. Again, infinite sum. We all understand where this infinity, the notion of infinity, came into physics, again using the very simple, very straightforward, nothing more beyond the typical middle school or maybe high school material. We understand how even at that level there is room or there is a need for the notion of infinity in physics. That is even without wading into deeper waters in physics. So what do we have here? Here we have one and the same term, square root of 2h0 over g. We can factor out square root of 2 times h0 over g. Factors out and becomes what? 1 plus 2. Here is the infinite geometric series that runs from 1 to positive infinity r raised to the power of k. And what does that mean? That means that we have our square root of 2h0 over g times 1 plus 2r over 1 minus r. Again, we know what will happen here. 1 minus r from the denominator will percolate into the numerator. It will collide with 2r, negative r, 2 positive copies of r cancel out nicely, 1 plus r. So now we can write down the result for the total time that our chicken spent airborne, and that time will be the square root of 2 times h0 over g times 1 plus r divided by 1 minus r. This is yet another result. And also, what do we see? That this quantity and this quantity are locked into which relationship? That our total time, total horizontal distance that is traveled by chicken before it stopped bouncing is equal to the total time. I try to use fancy font. From here, they lock into this relationship and the game is over. And again, here, just like in physics, just like in mathematics, no interesting problem is really solved. Just like, for example, they say that no painting is ever done. It is just walked away at an opportune moment. No book or no novel is really done. It just walked away at an opportune moment. In mathematics, no interesting problem in mathematics is done and completed. It is just walked away at an opportune moment. Here, no interesting problem in physics is done. Is just walked away from at an opportune moment. Here's an opportune moment to walk away from this problem. But what we can do? Well, remember we established the relationship between the trigonometric functions of tangents of the angles which our vectors make after each bounce. And we saw that this angle gets smaller and smaller every time until it also, so maybe you can invent another mathematical condition, not the limit. Remember how we operated. We said the limit of the nth maximal point must be 0. And that's how we came up from the problem in real analysis when r is strictly less than 1 raised to the whole positive on in the limit when n grows without bound is 0. Maybe you can discover or invent another similar mathematical condition that will translate stops bouncing with the angle of the vector. When the angle, for example, is 0, then evidently also the initial angle of the velocity of the chicken is 0. It means evidently it stopped bouncing. It cannot take off anymore. You can research this problem in this direction. In another direction, those of our viewers who are not shy with the keyboard can probably write an interesting software simulation where we will have how many parameters? H0, V0, and the value of our common ratio in our geometric progressions R. And depending on how we dial in these numbers, we can model the behavior of our material point as it bounces and stops bouncing, for example, in that direction too. And it looks like our chicken, spherical chicken of uniform density, will become a member of the permanent cast on this channel, and we will see this chicken again and again. For example, this chicken in the near future will try to slide off the top of the stationary sphere, and we will be asked to compute the time that it takes the chicken to jump off that sphere. In yet another case parabola goodbye, the same chicken will be misbehaving and sliding off the parabola, and it will jumping off, and then we will be asking all sorts of interesting questions. There is a Lagrangian hiding here, another Lagrangian hiding here, all beautiful, interesting stuff. But for now, we're done with the physics problem S3P2, and we will move on to a new challenge next. Our next challenge will be a problem in computer science, CS, problem number 2 of season 3. Remember that with the letter CS we designate problems in computer science, with the letter P we designate the problems in physics, and with the letter M we designate problems in mathematics. This will be a problem in computer science, consequently S3CS2, and the essence of that challenge is the following. Suggest Turing machine, TM, Turing machine-friendly algorithm or algorithms, if you know several such algorithms, for testing whether a given point, P, is located inside or outside of a given Euclidean triangle ABC. In other words, on the input into our algorithm, we will have 4 points, and it will be known, obviously clear, which 3 points delineate a triangle and which is the point to test. Or, because this whole affair unfolds in a plane, 2 units of information per point, altogether 8 units of information, and we need to determine with absolute certainty whether the point P is located outside of a given triangle or inside of a given triangle. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the problem S3CS2.